Section 6.4 is about partial fraction decomposition. So partial fraction decomposition is kind of the opposite of what we've always been trying to do in terms of getting a common denominator to be able to add or subtract fractions. Today what we're going to do is start with a fraction in the denominator and pull it apart into two separate pieces that we can then add or subtract. This doesn't really show up too often. There are a couple places in calculus that use it, but otherwise it is just a skill that we learn here and then we won't really see again. The reason why it's in this chapter is we can set up a system of equations to solve to get these numbers that would need to be on top of our fraction a and b. The good news is we don't really need to use a matrix to solve these systems. So it's not really a matrix type problem. We don't need to use matrices to solve it. The equations are actually pretty quick to solve, and there's a really easy way to do it when we only have two numerators like the first example here. So here's what the process looks like. The first step you want to do is to take your original denominator and factor it. So yes, we have to remember factoring from last year, Algebra 2, and break this down into two binomial factors. So for this, remember we always want to see what multiplies to be this last term, does whatever that sign is. So in this case, it subtracts to be whatever this term is. So we need two numbers that multiply to be 2, have a difference of -1. So those numbers would be -2 and +1. So those are the factor pairs that we make, x minus 2, x plus 1. If you need to shake the rust off on that, you can always double check your answer by foiling this back together and making sure that all the terms are what we originally had. For us, we've got this correct, so we can move on. Next thing we want to do is we want to just put placeholder variables on top of these denominators that we're going to split apart. So decomposition, breaking things apart. So we've got the first factor as a denominator. We've got the second factor as a denominator. Book always does A, B, C in order. Doesn't really make a difference whatever letters you want to put up there. These are what we're going to have to solve for. So if we were given something like this, what we would try to do is get a common denominator to be able to add it. And the common denominator, of course, is what we just factored, the x minus 2x plus 1. Then we would ask ourselves, what is each piece missing in the denominator, and then multiply the top and the bottom by that missing piece. So for the a fraction, this denominator is missing x plus 1. So we would want to multiply that piece, top and bottom, by x plus 1. Now we're not really concerned with the denominator. We know that it's going to come back to be the x squared minus x minus 2. So we just focus on the numerator, and we take this product. So a, x plus 1. Same thing with b. b is missing the x minus 2 in the denominator, so we will multiply both top and bottom by x minus 2. Again, we're really only concerned with the numerator, so we've got b quantity x minus 2. Now that we've got those, we know that the denominators equal the x squared minus x minus 2. The numerator needs to equal the original numerator, which was 2x plus 5. So we've got technically a system of equations. It's only one equation right now, but we still have two unknowns. And if we wanted to, we could do some distributing and then get the x terms and the constant terms, set up two separate equations, solve it like a system. But like I said at the beginning, there's a much easier way to solve this, and that is plugging in the zeros of the x's. So we find the numbers that would make each of these quantities 0. So for this case, the 0 is -1, and with the b parenthesis, the 0 would be 2. So those are the values that we're going to plug in. So when I plug in -1, we get a negative 1 plus 1, b negative 1 minus 2. We're plugging it in for all of the x's, so we plug it in on the right side of the equation as well. Again, why we're doing this is so we get zeros, so that becomes 0 and the a term goes away. With b, we have negative 1 minus 2, which is negative 3b. On the other side of the equation, we have negative 2 plus 5, which adds together to be 3. Last step is going to be to divide by whatever coefficient is on b. In this case, it's negative 3. We do that division, which means b is negative 1. So we've got our first value for our numerator. We do the same process again with the other 0 that we found, which is 2. So we plug in 2 for all of the x's. So we get x is 2 plus 1. B, the x is 2 minus 2. And on the other side, 2 times 2 plus 5. Again, this term will be a 0, which lets us figure out what a is. So 3a equals 4 times 5, which is 9, 4 plus 5, which is 9. So 3a equals 9. We divide both sides by 3, and a is 3. So now we've got our two numerators to plug in for a and b. The important thing here is that we put a back over the fraction where it started, so a goes over the x minus 2, and b goes over the fraction it was on, so we have negative 1 over x plus 1. As you start to do these problems, you may do them with the factors in a different order than somebody else, and that's okay. Your a might be 3 and theirs might be the negative 1. As long as they're over the correct fractions, it doesn't make a difference which order they're in. So if you set it up slightly differently, you're going to get the same numbers but kind of opposite letters, which is fine. Just put them back over the denominator that you started with. So that is the breakdown for the fraction 2x plus 5 over x squared minus x minus 2. Alright, so there's an example for you to try right here. I'm going to work through that, so if you want to try it, pause this video, scroll down, and try this problem. Alright, so for this one, we do have a leading coefficient that is not 1, so we need to remember how to factor that. I like AC factoring. There's also split the middle. If you really feel like it, you can guess and check. Whatever you need to do in order to factor this. So for AC factoring, remember that a is the coefficient of the first term, c is the constant term, so our a is 2, our c is negative 3, and a times c, 2 times negative 3, would be negative 6. So I need factors of negative 6 that have a difference of negative 5. Well, negative 6 plus 1 is negative 5. The only factors of 1 are 1 and 1. From the negative 6, I need to get factors that will let me make a 2 and a 3. And those factors, of course, are 2 and 3. If we look at the numbers in our original denominator, the 2 is positive, the 3 is negative. So that's where our negative sign goes. The last thing is we need x's and constants. We need a 2x squared in the original problem, which means this 2 has our x. Doesn't make a difference on the other side, they're both 1s, so that's an x. To finish off the AC factoring, we want to take an x from one side and pair it with a not x from the other. X from one side with a not x from the other. Those will be our binomial factor pairs. So we've got 2x plus 1 and 1x minus 3. Those are the factors of the denominator. So that's what we're going to use to set this up. We have a over 2x plus 1 plus b over x minus 3. If you wrote them in a different way, you might have a over x minus 3, b over 2x plus 1, and again, that is fine. Your a will be my b and vice versa. So this a fraction, the bottom is missing the x minus 3, so that's what we multiply a by, a times x minus 3. Don't worry about the denominators, that'll work out now that we've got it factored. The b fraction is missing the 2x plus 1, so we've got b times 2x plus 1. There we go. All right, and we set that back equal to the original numerator, so 11 plus x. Next thing we need to do is find our zeros. So for this first one with the a, 3 would make that 0. For b, we're going to have a fraction, so if we solve that, our 0 is negative 1/2. So those are the two x values that we want to plug in to be able to find a and to find b. So x equals 3 or negative 1/2. So let's start by plugging in 3 for all of the x's. So we have 3 minus 3, b times 2 times 3 plus 1. And on the other side of the equals, we have 3 plus 11. Again, so these are zeros, so the first term here is 0, plus 2 times 3 is 6, plus 1 is 7b, which is good because the other side is equal to 14. And when I divide by 7, I'm still getting a whole number, so our b is 2. Now we plug in 1/2, so I've got a negative 1/2 minus 3 plus b. This b part will become 0 in this problem, equals negative 1/2 plus 11. I'm going to keep it as fractions and improper fractions, not go to decimals or mixed numbers. So we've got negative 3 and a negative 1/2, so it'd be negative 3.5, but let's make that an improper fraction, so that's negative 7/2 of a. Again, that term will be 0. And on the other side, 11 minus 1/2 is 10/2. 10/2, 10.5. And 10.5 is 21 over 2. Since they're both divided by 2, I can just multiply both sides by 2, get rid of those denominators. So we have negative 7a is equal to 21. Divide by negative 7, and we get another nice whole number. A is negative 3. Those are the two values that we need. So then we finish this off by putting them over the denominators that we split. So negative 3 over 2x plus 1, and b, which was 2, goes over the x minus 3. That is the decomposition for x plus 11 over the quantity 2x squared minus 5x minus 3. All right, so we've got a couple more examples. We go back up to the top of the page, and we have an improper fraction. So if we notice, this one's a little bit different. The first two examples that we had a square on the bottom and then a linear factor, just x on the top. Here we've got a quadratic factor on the bottom, or quadratic polynomial on the bottom, as well as the top. So an improper fraction means the numerator is bigger than the denominator, so our 3x squared is bigger than x squared. So whenever we've got a improper fraction, we need to start by polynomial long division. We're going to only have to do one round, one time through, basically just to reduce that constant off. So for the polynomial long division, remember our top goes in the box, so 3x squared plus 12x plus 4, and the denominator goes on the outside, plus 2x. We're always asking ourselves, what do I need to multiply this outside term by to be exactly this term? So don't get it confused with the matrix elimination where we were trying to get opposite signs. For the polynomial long division, we need exactly the same thing, same sign and everything. So for x squared to be 3x, we want to multiply by 3. That's going to go in our constant column, which is right there. So we're multiplying 3 to both pieces here on the outside. So we would get 3x squared and 6x. Once we do that, we want to subtract which again is different than the matrices. We were adding, this time we're subtracting. So this first part should always be 0 as long as we picked the correct number. In this case it is. Then we have 12 minus 6x, which is 6x, and we bring down the 4. So at this point, that's a remainder, which is actually what we want. When we were doing the polynomial long division, the goal was to get factors that worked through cleanly and got us no remainder. This time we actually need the remainder because that is the fraction that we're going to decompose. So we take our remainder and we write it over the original denominator. So 6x plus 4 over that denominator of x squared plus 2x. This end fraction is what we're going to decompose. The 3 is just going to hang out. We don't want to forget about it. We need to bring it back into our final answer, but it's not going to affect the decomposition. So that's what we're working on. To factor the bottom, only 2 terms. So we're just looking for what is the same in both of those terms. We've got an x squared, we've got a 2x. So the term they have in common is just x. So that's what we will factor out of the bottom. We have an x, and then we get left with x plus 2. So these will be our 2 denominators when we split this fraction up, when we decompose this fraction. So our first over x, our second over x plus 2. Again, pick whatever letters you want. I'm just going with a and b because that's what the book does. All right, so at this point, we know that fraction is coming from the remainder piece, which was 6x plus 4. So we want to do the multiplication by what the denominator is missing, and then set that back equal to 6x plus 4. So the a fraction is missing the x plus 2. So we've got ax plus 2. The b fraction is missing just an x, so we've got plus bx. We set that equal to 6x plus 4. Now we need to get our zeros. So if we plug in -2, that will be 0. This one's a lot easier. It's just 0. Start by plugging in -2 for all of the x's. So we've got -2 plus 2 plus b times -2 equals 6 times -2 plus 4. That term is 0. We get -2b. 6 times -2 is -12. -12 plus 4 is -8. We divide both sides by -2. B is 4. Now we go back and plug in 0, which should solve for a. So we've got 0 plus 2. B times 0, which will be 0, equals 6 times 0 plus 4. So that part is 0. We get 2a equals 4, which means our a is 2. So the partial fraction decomposition part is the exact same as what we were doing in the first couple problems. We just have to start by using polynomial long division. So like I said, we don't want to forget the 3 now that we're going to write our answer. 3, which is what we divided out to start, and then the 6x plus 4 over x squared plus 2, that's what we just broke down. It became a, which is 2, goes over the x, and our b value, which was 4, goes over x plus 2. So that fraction decomposes to be those 3 pieces: 3, 2 over x, and 4 over x plus 2. So we've got one final example down here. This is the repeated factor. So if we look at this denominator, again, slightly different. This time we've got x cubed, and our other 2 pieces both have x. So we actually need to start by factoring out what's common to all 3 pieces. Again, all 3 pieces have x, so we start by factoring out an x. I get left with x squared minus 2x plus 1. This is a quadratic, and I can factor that apart. I need 2 numbers that multiply to be 1 and add up to be -2. So those would be -1 times -1. This is why it's called a repeated factor. This and this are the exact same factor. We see it twice. Another way that we could write this is quantity x minus 1 squared. So the factor is repeated. So when the factor is repeated, we do need to account for the fact that there are now 3 factors in the denominator, but we do have to do something special since one of them is the same as the previous. Here's what that looks like. So we've got 3 pieces. So it's going to be A, B, and now C. The first factor that we took out was x. The second factor will be x minus 1. And for C, this is where the trick, the little special part comes in. We don't just do x minus 1. Since it's a repeated factor, we do that factor squared, since it's the second time we're seeing it. So second time we're seeing it, it is squared. If we had more of the same factors, every time we see that factor, we put the next power on it. So if we had 5 of the same factor, it'd be over the first, that factor to the second, then to the third, and to the fourth, and to the fifth for our 5 successive pieces of the fraction. So whenever we've got a repeated fraction or repeated factor in the bottom, we show it up by itself. Next time we square it. Next time it comes up, if it does, we cube it, so on and so forth. From here, the process is going to be more or less the same. We are going to have to do another equation, essentially, to solve for that third letter. And this time, we have 3 parts of the denominator, so there's going to be 2 things that A and B are missing, but since C has a square already, it's really only missing 1 thing. The A fraction is missing the x minus 1 and the second x minus 1. So either way you want to write that as x minus 1 times x minus 1, or as I'm doing, just x minus 1 quantity squared. The B fraction is missing another one of those x minus 1's, as well as the x, which was the first thing we factored out. And finally, the C fraction is only missing 1 thing, since it's already x minus 1 squared. It's just missing an x. Just like before, we take all of that and we set it equal to the original numerator. In this case, it was x plus 2. Next step is still the same. We look for our zeros. We are going to get 2 zeros again, even though there's 3 factors. One of them is repeated, so I can't list that 0 twice. It's the exact same number. So what would make this 0 would be 1. Again, this is a repeated factor, so that's a 1 as well. So nothing new there. And then for the x, either C or the B part, 0 would make that 0. So we do technically have 3 zeros. We're only going to really use 2 of them because 1 is repeated. We can't use it twice. So we have x equals 1 or x equals 0. So if we plug in 1, we get A, 1 minus 1 squared, plus B, 1 minus 1 times 1, equals C, not equals, plus C, times 1, now equals 1 plus 2. So we're going to get a few zeros here. A is going to have a 0. 1 minus 1 is 0. B is also going to have a 0. 1 minus 1 is 0. C times 1 is C. 1 plus 2 is 3. No division required. There is our first solution. C is equal to 3. Do the same thing again, this time with 0. So we've got A, 0 minus 1 squared, plus B, 0 minus 1 times 0, plus C times 0 equals 3. This time the B is going to be 0 and the C is going to be 0. 0 minus 1 is negative 1, but negative 1 squared is positive, so we just get A is equal to 2. I messed up there. It's not 3, it is 0 plus 2, which is 2. So A is 2. Right, so we have our first 2 solutions. I need to pick another number to plug in to be able to get b. I've already used 0 and I've already used 1. If I go back and use 1 again, that repeated factor, nothing is going to change. I'm going to get the same result as I got right here. The b part will go away and I'll just get c again. So I actually need to pick a different x that's pretty arbitrary. So I can really pick any x that I want that is not 1 or 0. These equations are true for all x. They're only one variable, so whatever x I pick is going to make the equation true because I'm solving for b. So I know everything but b. I know what c is, I know what a is. I just pick a random x, which will let me solve my last missing letter, which is b. So it's best to pick a small x value. Positive is usually better. So we've already used 1. We can't use 0 either, so let's go with 2. So we're going to just arbitrarily, out of the blue, pick x is 2. It's a smart choice. It's not completely random. It's a small number, so we pick 2. We're plugging in 2 for x. We're also going to plug in the value for c and the value for a that we already determined. So a was 2. The x we pick is 2 minus 1 squared plus b, which is what we're trying to solve for. The x that we picked is 2 minus 1. The x that we picked is 2. Plus our c that we found is 3. The x that we're picking is 2. Equals 2, the x that we picked, plus 2. So we've got just one unknown quantity, b. This should solve for b. It will solve for b. 2 minus 1 is 1. 1 squared is 1, so we've got 2 times 1, which is 2. With the b, we've got 2 minus 1, which is 1. 1 times 2 is 2, so we've got 2b. Plus 3 times 2 is 6. On the other side, 2 plus 2, that is 4. All right, so we just finished solving with the algebra. We get 2b plus 8 equals 4. Subtract 8 from both sides. We get 2b is equal to negative 4. Then we finish by dividing, so b is negative 2. So there is our third solution. B is negative 2. So I'm going to move back to the left here, and we're going to plug all of that back in just to finish this out. We do always want to write our values that we found over the parts of the denominators. That's how we finish this problem. So we have 2, negative 2, and 3. And that is what our fraction breaks down to be. So this, we're skipping right here. It says skipping in your notes. Nonlinear repeated factor. Just very briefly why we're skipping it. If we look at this denominator, that is a non-factorable quadratic. I would need two numbers that multiply to be 1, but also add to be 1. That's not possible. So what would happen is when I have that repeated nonlinear factor, my numerators get more complicated. Instead of just a number, it has to be like ax plus b. Since the bottom is square for our factor, we always go one less power. So we have an x in the numerator now, 2 terms. So we're going to end up with something like 4, maybe 5 equations to solve for these different letters, a, b, c, d, so on and so forth. So that becomes a pretty big system. It's not super hard to solve for it. Usually one of the letters is found right away, so usually one of the equations results in like, d equals 4 or a equals 7. And we get a number right away, and then we start back substituting, and the solutions sort of fall into line. But it is a lot bigger than any of the systems we've been solving. We're not going to see this one. It's not in the homework. It won't be on the test, so we are just going to skip that one. So if we look back at this, those are the 3 that you should be able to do. They all basically become the same process with a little different start. So for the improper fraction, start with polynomial long division. For the repeated factor, we have to recognize it's repeated and then make sure we account for that with the denominator and squaring it.